While Tesla continues to cap the Model Y's charging rate around 2C in the name of long-term durability and system stability, Chinese automakers have moved far beyond that conservative boundary. Several mass-market EVs in China now sustain 4C charging, cutting real-world charging times to roughly 15 minutes. More importantly, the world's largest battery manufacturer has now introduced a 5C battery system explicitly designed to maintain performance not just at launch, but across the usable lifetime of an electric vehicle. As an electrical engineer who has worked directly with lithium-ion degradation models, I can state this plainly at 5C. Most automotive batteries on the road today would collapse rapidly. Severe lithium plating, accelerated SEI growth, cathode cracking, and thermal stress would destroy usable capacity long before reaching even 1,000 cycles. Yet CATL is claiming a cycle life roughly 6 times higher than today's industry average. That forces a much sharper question than does fast charging hurt batteries. The real question is whether the limits we have trusted for years are still valid. At a fundamental level, what does 5C actually imply? For an 80 kilowatt-hour battery pack, it corresponds to nearly 400 kilowatts of charging power and a theoretical full charge in roughly 12 minutes. Historically, even brief exposure to 2C or 3C charging was enough to accelerate irreversible damage. This is why most EVs today exhibit dramatic power tapering shortly after plugging into a high-power charger, even when the station itself can supply 300 or 350 kilowatts. The bottleneck has never been infrastructure, it has always been chemistry. CATL is claiming that bottleneck no longer applies. Crucially, this claim does not rely on a single miracle material. Instead, CATL is attacking the core degradation mechanism simultaneously. A more uniform and mechanically stable cathode coating reduces stress concentration as lithium ions move rapidly in and out of the lattice. This matters because microfractures are not cosmetic defects. They permanently isolate active material and accelerate electrolyte breakdown. CATL's electrolyte formulation includes proprietary additives designed to reform the SEI layer at microcrack sites, reducing irreversible lithium loss, the primary driver of capacity fade under fast charging. The separator itself is coated with a temperature-responsive material that locally restricts ion flow when heat spikes occur, acting as a passive safety valve before thermal runaway conditions can form. If these mechanisms behave as described under real-world loads, the implications are profound. Battery management systems today aggressively limit charging power, not because they want to inconvenience drivers, but because they are compensating for chemical fragility. If the chemistry itself becomes resilient, the BMS no longer needs to be conservative. That alone explains why this announcement creates discomfort across the industry. Thermal performance is where CATL's claims become impossible to ignore. Under ambient temperatures of 60 degrees Celsius, conditions typical of summer operation. In parts of the Middle East, the battery reportedly retains 80% capacity after 1,400 full cycles. For conventional lithium-ion packs, this combination of heat and fast charging is essentially a death sentence. Elevated temperature accelerates every degradation pathway simultaneously. If CATL's data is accurate, high-temperature operation ceases to be a special case risk scenario and becomes a manageable design parameter. From an engineering standpoint, the logical conclusion is unavoidable. Battery life is no longer the primary design constraint for electric vehicles. 3,000 cycles, even at a conservative real-world range of 500 kilometers per cycle, still equates to more than 1.5 million kilometers of usable service. Very few vehicles will ever reach that distance before being retired for reasons entirely unrelated to the battery chassis fatigue, suspension wear, corrosion, or accident damage. That raises a question the industry has so far avoided. If batteries are no longer the weakest link, why are warranty terms still anchored at 8 years? Why are charging curves still aggressively throttled? The answer is not chemistry, it is institutional inertia. CATL is not positioning this battery first for private owners. It is targeting taxis, ride-hailing fleets, delivery vehicles, and heavy-duty electric trucks machines that charge multiple times per day under demanding duty cycles. This is not a marketing experiment. It is a stress test under the harshest possible usage patterns. If a battery can survive that environment for years, then light-duty consumer use becomes trivial by comparison. The economic consequences follow directly. Battery replacement has been the largest unresolved liability in EV total cost of ownership. A $15,000 to $20,000 pack replacement instantly erases years of fuel savings and destroys residual value. A battery capable of surviving the entire operational life of a vehicle eliminates that risk. Used EVs stop being speculative purchases. Fleet operators can amortize battery cost over decades rather than years. High-utilization electric platforms suddenly become structurally cheaper than internal combustion alternatives. This is also why the implications extend beyond individual vehicles to the broader automotive market. When internal combustion engines routinely failed before 100,000 miles, rapid vehicle turnover was normal. Japanese manufacturers changed that paradigm by proving that 200,000-mile engines were economically viable. The result was a longer ownership cycle and a fundamentally altered used car market. CATL is applying the same logic to energy storage, but at an even larger scale. If electric vehicles routinely last twice as long as their internal combustion predecessors, global demand for new vehicles will inevitably decline. Fewer replacements are needed each year. That is not a comfortable outcome for manufacturers built around volume growth, and it explains why longevity is discussed cautiously, even when the technology supports it. Software-defined vehicles accelerate this shift further. Over-the-air updates allow drivetrains, efficiency profiles, and driver assistance features to evolve over time. When performance and functionality improve instead of degrade, the only remaining life-limiting factors are structural. Corrosion resistance and mechanical durability become more important than battery degradation. This context also explains CATL's parallel push into sodium-ion technology. Sodium-ion batteries offer excellent low-temperature performance, high tolerance for fast charging, and intrinsic resistance to thermal runaway. CATL has already begun production for light commercial vehicles and is expanding into passenger car testing in cold climates. According to the company's CTO, sodium-ion energy density could approach LFP levels within 3 years, while achieving roughly 1/3 lower cost at scale due to sodium's abundance and supply chain stability. From a systems engineering perspective, sodium-ion does not need to outperform lithium everywhere. It only needs to dominate specific operating envelopes, cold climates, high-cycle applications, cost-sensitive segments. Combined with long-life lithium-based 5C cells, this creates a diversified battery portfolio that reduces both technical and geopolitical risk.